Hello everyone. So welcome to our experiment number 4, that is shifting, scaling and reversal of periodic signal. And then we'll talk about Fourier series as well. So as shifting, scaling and reversal is already been covered in the theory class. So in this class, we'll mainly verify the things, and that is we will verify the theory part using MATLAB coding. Okay. And first, we'll talk about shifting, scaling, and reversal of periodic signal. After that, we'll go for Fourier series. Okay, so let's start. Now, at first, let's have recap about the three properties of a signal: shifting, scaling, and time reversal. So, if we consider that we have a signal x of t, that is, say we have a function x of t. So this is the signal, and x of t minus t naught, that is minus t naught, it will ensure that the signal xt will be shifted towards right direction by t naught. Again, x of t plus t naught, it will ensure that the signal x of t will be shifted towards left direction by t naught. Forget about this image, this is erroneous. So you know the basic. Okay. So let's proceed for time scaling. Let's consider that this is our signal x of t, which will start from, which will have 1 from -2 to 2. Now, if this t, if we multiply anything with t, so let's consider x of 2t, then the signal will be compressed. And if we divide time t with 2, then the signal is being expanded. So the bottom line is, if you want to multiply t with any constant value higher than 1, then your signal will be compressed, and if you divide it, then your signal will be expanded. So this is the properties from time scaling. And then the last one, that is time reversal or reflection. It's very simple. Say if we have a signal x of t, as you can see from the figure, that this is your signal x of t. Now the time reversal will just give you a mirror reflection of your signal x of t. So this is your signal x of t. Mirror reflection of this signal will be x of minus t, which you can see that exact mirror reflection. So these are the three properties which already have been discussed in the theory class. Just I have discussed it so that it will be easier for you to recall, and it will be easier to correlate with the coding part. Now we will move to the coding part, and we'll try to verify these three properties. Okay, so as we have seen, to perform these properties, at first we need to define a signal, or at least we need to have a signal x of t. So in the coding part, first we will see how we can define a signal, and then we will verify these three properties. Okay. So this is the editor. There is live editor. You are already familiar with live editor, right? So let me enlarge the font. So hopefully it will be easier for you to understand now. So in the coding part, first what I will do, so we will see how we can define exponentially damped sinusoid, also unit step function. So at first we will see how we can in fact uh, represent different types of signal x of t. So we'll first generate x of t, and then we'll perform we'll check these three properties on those generated signals. Okay, so here you can see this section, and in this section we have generated one function x of t. So please look at the code: clear all, close all, and then x inline exponential minus t cos twice by t. So this is the function. This is exponentially decaying sinusoidal function. Okay, the sinusoid is here cos. Okay, so exponentially decaying cos function, or you can say exponentially damped sinusoid, and here the variable is t. So x inline, this inline is being used to define the function, and this t is indicating that the variable will be t in this function. The variable will be t. So let us run this code. Okay, and the time we are varying is from 0 to 10 with an interval of 0 0.01, and then we just plot it. So let's run this part. So as you can see in the right side, we have the plot of exponentially damped sinusoid. So again, I'm just giving the recap. That is, in this line, x inline exponential of minus t into cos twice pi t. With this line, we just defined the exponentially decaying function where t is the variables. And now when we vary t from 0 to 10 and then plot this t of x t, then this plot has been generated. So now this is one approach we can generate, we can plot the function x of t. And uh, so x inline, this is one way where we can define a function. There is another way. So the second approach is more or like similar, just one difference. Instead of inline, you can simply use this notation. So you will have the same result. Okay. So here you are saying that t is your variables, and then the same functions we have just defined. So both the case will give you the same results. So you can see for both of them you are having the exact result. So the intention was to tell you that you can define your function in different ways. So we have shown you two ways there. Okay. So now again we will see how we can produce unit step function in MATLAB. So before before producing that unit step function, let us just recall what is unit step function. Okay, so a unit step function, let me show here. Okay, so uh, for unit step function, let's say this is our time t, and this is the axis u of t, the axis u of t. So for unit step function, whenever time t is negative, that is less than 0, that time u of t will be equal to 0. So for this phase, that is negative time, u of t will be 0. And whenever time t is equal to 0 or positive, that is whenever time t is greater than or equal to 0, that time u of t will be equal to 1. U of t will be equal to 1. That is the unit step function. Okay, so now let's see how in MATLAB we can generate this type of function. So this is the code. Before explaining the code, let me just run it. Okay. So here it is. You can see the unit step function. As I have said already that this is our time axis t. So for any time less than 0, u of t is equal to 0. But whenever time t is equal to or greater than 0, that time u of t is equal to 1. So this is unit step function. Now let's see how we have generated this. So here you can see in here u is defined in terms of t is greater than or equal to 0. So please try to look at this point. Here, this is a condition. This is a condition. So this condition is checking the value of t, and if this condition is true, then this due to this condition, if this condition is true, you will have 1. If this condition is false, sorry, if this condition is false, then you will have 0. Okay, so u is nothing but a single array. So and this array is checking, in this array first this condition will be checked. Okay, so first t first we will check this condition, and depending on the condition, if it is true you will have 1, and if it is false you will have 0. So let's see this. Okay, let me explain this here. So our time t is varying, say from -5 to 5. So as you can see in the coding as well, our time t is varying from -5 to say interval to 5. Now u is equal to this notation, and then t, and then the condition t is greater than or equal to 0. So how from there how we can have this type of unit function? Let us check. Let's check 2 point here, say for -5 and say for -1, and then we will check 2 condition here, 0 and say 2. Okay, so whenever time t is equal to -5, then this condition -5 and 0. So -5 and 0, so 0 is greater than -5. That means this condition is not true. So as this condition is not true, or we can say as this condition is false, so it will produce 0. As a result, u will be equal to 0. So you see at this point u of t equal to 0. Similarly, when time t is equal to -1, -1 is less than 0, -1 is less than 0, so this condition is false. As this condition is false, so u will be equal to 0, u will be equal to 0. That's why you can see u will be equal to 0. So for all the cases, whenever time t is less than 0, this condition will be false and u will be equal to 0. Now, when time t is equal to 0, then 0 is equal to 0. 0 is equal to 0. As a result, this condition is true. So you can see u is equal to 1. So at time t is equal to 0, u is equal to 1. Again, when time t is equal to 2, 2 is greater than 0. So this condition is true. So u equal to 1. You can see u equal to 1. That's why whenever we write this line, then we are actually, and whenever we are varying the time t, then we can have the unit step function. So let's again just check. This is the function, and time t is varying from -5 to 5. And then whenever we are plotting t u of t, it is just giving us the unit step function. Fine. So as I have said that at first we need to generate the function, and then we will check the properties. So already we have generated 2 functions. One is exponentially decaying sinusoid, another is unit step. So we have the function x of t with us. Now we can verify different properties. So let's first verify shifting and time reversal. So we have u of t. Remember, this is our u of t. Now u of t minus 2. Okay, let me first remove this comment after this. So u of t minus 2, as I have already said, that t minus 2, that is t minus something, it will ensure that the function u of t is being shifted towards right direction. So if we consider that this is our the x-axis, or the time is in second, if the time is in second, then we can say that u of t minus 2, it will ensure that the whole signal u of t will be shifted towards right direction by 2 seconds. And u of t plus 1, it will ensure that the signal will be shifted towards left direction by 1 second. So let's verify. So this is our u of t, and u of t minus 2, this one, and u of t plus 1 is this one. You can see minus 1 here because the signal has been shifted towards left direction by 1 second. So we have verified the shifting properties. Now we will also verify the time reversal properties. So you already know that time reversal properties is nothing but the mirror reflection. So if it is our u of t, the mirror reflection of this, that is u of minus t, will be simply this, right? So let's check. This is u of minus t. So if we run it, you can see that we are having the mirror reflection of u of t. So that is, we have now also verified the time reversal properties. So shifting is done, reversal is done. Now only remaining is scaling. So let's check. We have the signal. Now let's consider that, okay. Now let's verify the time scaling properties with the help of sinusoidally decaying signal. So this is ours. Let us first give their comment. Just run up to this. So here you can see that we have exponentially decaying function. We just plot it. Where it is. Oh, sorry. I just use the comment for the plot as well. So let's remove it, and now let's run. So we have sinusoidal decaying cosine function here, that is x of t. Now if we write x of 2t, according to our understanding, the signal should be compressed, and x of t by 2, if we perform this, then the signal will be expanded, right? So the signal is supposed to be expanded. So let's check. Okay, so this is the case. We have x of t and x of 2t and x of t by 2. So our original signal x of t, compressed signal, expanded signal, that is the time scaling properties. So we have, so far what we have done, we have produced the signal, that is exponentially decaying signal or unit step signal. Then using those signal, we have verified time shifting, scaling, and reversal properties. So first part of our today's lab is done, shifting, scaling, reversal. And then we are supposed to demonstrate the Fourier series. That is, we will actually verify the concept using the coding. Okay. So I will move to that. Just I want to show something. So last day I have also recorded the class. Okay, so last day I have also recorded the class, and this was the class lecture, but unfortunately there was no sound because unfortunately I have pressed the mute button of my laptop. Okay, so I'm really sorry that I am a bit delayed to give you the recordings due to this issue. So sorry for that. So hopefully today it will be okay and you can have both the audio and video in the recording. Okay, so let's again proceed. So first part of our lab is done. Now, the next part is Fourier series. So as you know that we uh, we implement Fourier series in periodic signal, right? So before moving to the Fourier series, let us first see that how we can define periodic signal in MATLAB. So that is, you can see the figure, right? In the x-axis we have t, in the y-axis we have x of t. So this is a periodic signal which is moving like this, which is nothing but triangular wave, right? Now this signal is being defined with the help of equation. So let us check. So this is the equation, x of t 4t for 0 to, sorry, for 0 to 0.25. So you can see for 0 to 0.25, this is x of t for 0 to 0.25, and then 0.25 to 0.75, which is 2 minus 40. So this is the 2 minus 40 line, and then from 0.75 to 1, it is actually, if I'm not wrong, 40 minus 4. Okay, 40 minus 4. So this is 40 minus 4. So we have given the equation. Now we are supposed to plot this in MATLAB. So it should be very simple, right? Why I am giving that much emphasis? Let's move to the discussion, then it will be more easy to understand. Okay. So this is the function we are talking about. X of t, in the x-axis we have t, in the y-axis we have x of t, and we are told that from 0 to 0.25, that is from 0 to 0.25, this line will follow xt is equal to 4t. So for the time being, I will discuss about this line. This same case will happen for this 2 as well, and we will see some problem, and then we will see the solution of that. So the same problem will arise also for this 2 line, and the same solution will be also applicable for this 2 line. So please try to focus only up to this discussion for the time being. So for the time being, let's consider that t is 0 to 0.25. So this part, for this part, our function xt is equal to 40. Fine. So this is our whole time period. This is 0.25, this is 0.5, this is 0.75, and again this is 1, and again 1.25, and then 1.5, 1.75, and then 2, right? And then again it should be 2.25, like this one. So if we consider that time t is equal to 0.2, that is anything here, say 0.2. So x of 0.2, it should be 4 into 0.2 equal to 0.8. Okay, let's check. So it should be something here, right? 0.8. Fine. And this is our periodic signal. Total time t is equal to 1 second. Fine. Now, if we consider 1.2 in this equation, if we consider 1.2, then 4 into 1.2 is 4.8. However, if we see that after one period, it should be again, we should have the same cycle, right? That is, if you want to have the same cycle at 1.2, we should also have 0.8, right? but we have 4.8 here because we are using this equation 40. 4 into 1.8 is 4.8. But if you want to have periodic signal, then it should be 0.8. So there are some issue. Similarly, if we just want to see that after 2 cycle, so t is 1 second again. After 2 cycle, if you want to say that okay, at 2.2, if you use this equation, then it should be 4 into 2.2, 8.8. But it for the periodic signal, it should be again 0.8, right? So I believe you have understood the problem. So let's again discuss that as this is periodic signal, we want that for time t is equal to 0.2, 1.2 or 2.2, after the single time period, the value should repeat. So for 0.2, for 1.2, for 2.2, all the case, it should be 0.8. But if we use this formula, then the values are different. So how we can resolve this issue so that we will have periodic signal, or after the time period, the same signal will again repeat for the second period. So the solution can be, if we can ensure that for time t is equal to 0.2, 1.2 or 2.2, for all the case, if we convert this value into 0.2, then if we just insert it into our function, that is 40, then x of 0.2 will be 4 into 0.2 is 0.8. So this can be a solution. For this, we have to ensure this, that whatever the time t, 0.2, 1.2, 2.2, let's just convert this into 0.2. How we can do so? We can use one built-in function in MATLAB, that is mod. Okay, so let's see, z is equal to mod x comma y. So what is the function of this mod? Let's say that okay, this is x, this is y. So this is x dividend, y is our divisor, and z will be equal to the remainder. So this is actually quotient of result after the division. So let's see example that mod 0.2 comma 1. So 1 is the divisor, 0.2 is the dividend, 1 and then 0.2. If we divide, result will be 0 and remainder is 0.2. That's why you can see that result is 0.2. Okay, done. This to this done. Again, if we check that for 1.2, this is 1. This 1 should be in fact your time, and that is time period t. So for our case, it was 1 second. That's why we have even 1. Now, divisor is 1, dividend is 1.2. If you divide, result will be 1 and remainder is 0.2. So again 0.2. That means even 1.2 can be converted to 0.2. Similarly, 2.2 can be also converted to 0.2. That means that after the time period, after the first time period, if you move to the second time period, you can actually have the same values. What I'm trying to say that okay, if you can ensure that time t is equal to 0.2 and 1.2 and 2.2, all the case you can ensure 0.2, then you can have the periodic signal, right? So what this mod will do, that after the first time period, again for 1 to 2, you are actually having time t is equal to 1 to 2, but it will be again due to the mod operation, it will be in fact converted to 0 to 1. Okay, so how this 1, so if you just see that what I have said, this 1 will be again converted to 0, this 2 will be again converted to 1. How? You see, if I say that fh double prime mod 1 comma 1, it will give you 0. How? Because 1 divided by 1 is equal to 1, so output is 0. That is, the remainder is 0. So similarly, if we check that fh triple prime is equal to mod 2 comma 1. Okay, okay, sorry. This one will be this 0. Okay, in fact, this is 0. Also, this should be also 0. So that's why it should be 0. Let's check. So your divisor is 1, your dividend is 2. So result is 2. Again, you have remainder 0. As a result, you can see this will be 0, this will be 0, this will be 0. All the cases, these points will be 0. And this point will be 0.25. This point will be also considered as 0.25. This point will be also considered 0.25. As a result, you can actually have the repeated signal even after the first period. Okay, so that is the main goal of your mod function. So now let's move to the coding. You can just have the few lines already written there. You can just go through to have a better idea about mod function if you do not understand yet. So let me just run this code. Let me run this code. So if we run this, we are supposed to have the periodic function. So yeah, this is our periodic function, which we have generated with the help of mod that we have discussed. So this is the code. Let me increase the size. So this is the code I have just copied to the MATLAB. So please have a look and try to understand that why this code is being written and how this is giving us the periodic signal. So you see our function is 40 for time 0 2.25 and t minus 2 minus 40 for 0.25 to 0.75, again 0.75 to 1, it should be 40 minus 4, right? So this is our function and we have just incorporated this function in this line. Rest of the things is easy. Okay, so you see 40, it's simple, mod t comma 1 into 4. So it is actually 40. I'm not discussing this part now. I'll discuss it about just after a few times. So this is your 40 done. T minus 40. So here we have done what? First we ensured minus 40. You see mod t comma 1 into minus 4. That is minus 40 plus 2. So this one just ensuring to this 2 minus 40. Now, again 40 minus 4. So mod t comma 1 into 4. That is 40 minus 4. Okay. So done. Now why this is written? Mod t comma 1 is less than 0.25 or this one is 0.25 greater than 0.25 less than 0.75 and this one greater than 0.75 less than 1. Why it is written? It is just ensuring that for a time t only one value will be calculated. You see, this is your equation, right? So this equation, this is equation, and this equation has so xt has three parts: 40, 2 minus 40, and then 40 minus 4, right? So just those they this part, the second part is just ensuring that at a single time only one of this equation will be used and rest of the two will be equal to 0. How? Let's say that our time t is equal to 0.5. I'm repeating again, our time t is equal to 0.5. So time t is equal to 0.5 means this should be in action, right? 0.25 to 0.75. So this equation should be in action. So you see time t is equal to 0.5. As time t is equal to 0.5, so this one will be equal to 0.5. So then this condition is false. Again, as time t is equal to 0.5, so even though, okay, so as time t is equal to 0.5, this condition will be also false. Okay, only the second condition, this condition will be true, that is 0.5 is greater than 0.25 and less than 0.75. This condition will be true. As a result, it will give you 1 into 2 minus 40 will be equal to 2 minus 40. That's why only this condition will be applicable and value will be calculated accordingly. So that's the thing. Even if you do not understand, don't worry. Try to consider some of the value of t and try to plug in by your own. You will get more clear idea about it. Okay. So now let's proceed. So that's how this is our code, and if you understand the coding, then hopefully it will be easier for you to understand that okay, how we have generated this time periodic signal. Done. So we have done by producing the periodic signal. Now we will go to the Fourier series, and it will be our last part for today's lab. So let me make it smaller. So now we'll talk about Fourier series and then Gibbs phenomenon. Okay, so what is Fourier series? Now, if we have a signal, if we have a periodic signal, any type of periodic signal, if you have in time domain, this signal is nothing but summation of sine and cosine with different frequency component, right? Let's see one. From this equation, you can also understand that if you have a time domain signal x of t, if you have a time domain signal that is x of t, you can represent that time domain signal with different frequency component starting from 1 to infinity. And this is actually for DC component for frequency is equal to 0. And other than that, k is equal to 1 to infinity for different frequency component. You can have time t as a summation of cos and sine. Okay, so let's try to visualize the thing what I'm trying to say. Suppose this is your time domain signal x of t. This is your time domain signal x of t. And if you consider different frequency component, and if you add all of them, then you can see you are retrieving back your original signal, which is shown in blue color. So the more you are taking the frequency component, the more accurate it will be to your original signal. Here the black color is your uh, original signal and blue color is your retrieving signal from the Fourier series. So the more frequency component you consider, the more these two will match. So if you let's see that for the first case we only consider one frequency component. That's why it's very much similar. One is sinusoidal signal, another is square wave. But whenever we are increasing the frequency component, then it is matching. The more you are increasing the frequency component, the more the retrieved signal is equal to the original signal. So now what will be our task today? Our task will be we will demonstrate this. We'll demonstrate this, that first we'll define a signal x of t in the time domain, and we'll perform the Fourier series of that signal. So by doing so, we'll try to find out different frequency component of that signal. So this is our time domain signal. We'll perform the Fourier series on that signal. So as a result, we will have different frequency component. That means at frequency say k is equal to 1. So at 1 hertz, we'll see what is the amplitude, what is the phase. Again at 2 hertz, what is the amplitude, what is the phase. At 3 hertz, what is the amplitude, what is the phase. So we are finding out different frequency components, that is amplitude and phase. Our time domain signal perform the Fourier series, find out different frequency components. This will be our first task, and we will see each of the component, and then we'll try to add all of them, and we'll try to retrieve back signal xt prime, and we'll see how much these two match. Okay, the more the frequency component we'll consider, the better match these two should have. This will also verify. So let's try to again understand what we are going to do today. First, we'll have xt, we'll perform the Fourier series, we'll see the frequency components, and then we'll add all of them, and we'll retrieve the signal xt prime again. So this will be our goal, and for that, just we need this equation. First of all, this is the equation we already know. That is the basic equation of Fourier series. So if we from this equation, if we just follow the derivation, I'm not describing the derivation, then you can come up this format as well. So the equation can be represented in different way. So this is one way, and we will follow this this representation because the question for this. So one problem is defined using those equations. That's why I will discuss. I will use this equation. Okay. Here ck is bk minus jak by 2, and ck, this is just the conjugate of the previous one. Okay. Now the question I am discussing, in this question they have given us the time domain signal x of t, and also if we want to find out the Fourier series of this time domain signal, what should be ck is also mentioned. Okay, so we know xt is equal to c naught ck to the power jk omega naught plus ck conjugate to the power minus j omega naught. This we already know. So from the time domain signal, so our task will be first plot this time domain signal, and then using this equation first, we will try to find out different frequency components for different value of k, and then we will add them to retrieve back our xt. So I'm repeating again. At first we'll plot the signal xt. We'll plot the signal xt, and then using the equation that is this equation, for different value of k, we'll see what is the response. It is how the signal is looking for different frequency. K is equal to 1, k is equal to 2, k is equal to 3. Okay, so after that I want to retrieve back the signal. So just add all of them. You see the summation sign is there. So what we will do, we'll just add all of them, and we'll find out the xt prime. Okay, this will be our target. So this is the code. Sorry. So first, let us run up to this first. So here you can see the time is varying from 0.25 to minus 0.25 to 0.25, and then 0.25 to 0.75. So that's why in the coding, minus 0.25 to less than 0.25, that's like 0.249, again 0.25 to 0.75. These are time, and x1 is 41, x2 is 2 minus 41, as mentioned in the equation, 2 minus 40. Fine. So we have x and t. Just we just prepared our signal x and time t. So if we run it, you can see that our x of t will be ready. So let's run it. So this is our x of t. Now what is our next goal? Our next goal is to find out that for different frequency, what is the signal? Okay, or the thing is, if we just try to uh, find out what are the frequency components available in this signal, we'll try to find out. Okay, so let's move. Let me first run this section. So now you see we have defined C zeros and comma length of t. So length of t is here you can see 1001. So minus 0.4 uh, okay, minus 0.25 to 3.75. In between we have in fact 1001 number of data. That's why here it will be n comma 1001. Okay, so what is n? Let's consider that n is equal to 5 for the time being. That means n is equal to 5 means I want to check 5 frequency component, 1, 2, 3, 4, 5. Okay. So we'll check 5 frequency component. So C is nothing but this one. Just consider that this equal to C. So for k is equal to 1, we'll store this value inside C, which will have total 1001 number of data. Like this 1, 2, 3, 4, 5, 6, 7, 8, then 1001. Okay, from 1 to 1001, this amount of data will be available in this plot. Similar case will be happen for others as well. So this is our C. At first for k is equal to 1, we will plot it, and then for k is equal to 2, we will plot it, k is equal to 3, we will plot it. So let's see how we are doing so. So CE zeros and comma length t, this is done. Initially we defined C is equal to 0. Initially all of them we considered as 0, all of them. Now for k is equal to 1 is to 9. Now we are checking the we are moving k from 1 to 5, and this is actually nothing but ck that is given. This is our ck already given, so we just mathematically represented this ck here. Ck we just write here as d, so this is actually the d. Fine. Now you see we for this problem let's consider c naught is equal to 0. Done. Now at k is equal to 1, at k is equal to 1, this is, we will find out the summation of this. For k is equal to 1, we will find out the summation of this. For k is equal to 2, we will see the summation of these two. For k is equal to 3, we will find out the summation of these two. So for k is equal to 1, first summation of these two, real part of this, and then conjugate into this. Okay, so I'm sorry, so real part of this function. Fine. So for k is equal to 1, we will check it and we will plot it, and then again it will move to the loop. Again k will be equal to 2, and then this will be added. And so at first for k is equal to 1, after the summation this plot will be this data will be available, and then we will plot it. Again for k is equal to 2, this data will be available, we will plot it. K is equal to 3, same case. So let's run up to this now. So you see for k is equal to 1 to 9, we have different lines here. This is actually for k is equal to 1, and for k is equal to 2, we have 0. For k is equal to 2, we have 0. That's why the line is this. So let us check C, then things will be more easier to you. Our C, and this is the plot from C. For k is equal to 1, these are the data, and the plot is the blue one. But for k is equal to 2, I have said that the value is 0. Why? You see 10 to, it is minus 33, it is minus 19. So those are nothing but zero. That's why you can see one straight line in the uh, axis, that is y is equal to 0. And this is the line. Again, for k is equal to 3, we have some data available. So the yellow line is for k is equal to 3. For k is equal to 4, again 0. And for k is equal to 5, we have the green line. Okay. So this these are the different frequencies. These are the graph for different frequency component we can consider. Okay. Now we want to retrieve back our signal. So one thing we can easily do, just add all of them, and then just check. So here in this code, they just used CumSum. That's why I wanted to explain that. Either you can manually just add all of them, it will be okay. Or just what they have done here, just used CumSum. So let me just explain that one as well. So let's say that H is your matrix 1, 2, 3, 4. CumSum will do what? That it will perform the cumulative sum. So 1, 2, nothing to add previously. So 3, 4 in this line, 1 plus 3 will be equal to 4. 2 plus 4 will be equal to 6. And again, for this line, 1 plus 3 plus 5 equal to 9. 2 plus 4 plus 6 will be equal to 12. Okay. Fine. So this is the basic about CumSum. Now, xn cumulative sum C, that is, we have defined another function x of n, so xn, which will have the cumulative sum of C. That means we consider this function. So nothing special. So first one, nothing to add. Second one, this plus this, as this is equal to 0. Again, you will have same thing. And then the third one, you will have the summation of these two, this plus this, these two. So maybe I don't know, maybe it will be more like this. And then again, this plus this plus this plus this, it will be same as this, because this is nothing but 0. So let's consider, and then the summation of all of them will be here. So maybe something like, so this is for k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, k is equal to 5. Okay. So again, you don't need to do this, you just add all of them and then just show this, it's also okay. So no need of cumulative sum, just it was shown in the lab report, that's what I'm saying. So now, after the execution of this line, what is the updated k you have? 1, 2, 3, 4, 5. So your updated k is equal to 5. You have performed the cumulative sum. So cumulative sum you have performed, and your k is equal to 5 is holding this value, summation of, remember this is actually the summation of all of them, right? Summation of all of them. So you have k is equal to 5. And if we just plot it, so you see tx and k comma 1. So k in this point is already having 5. So the last plot that is having the summation of all of them. Now if you just plot it, let's see what will be the output. Run and advance. So this is the output. You see xt, and then summation of different, and this is actually the different frequency component, and summation of all of them is giving me xt prime. Now this is not matching. This is not matching because we have considered few samples. If I increase more frequency component, sorry, if we consider more frequency component, then you will see that xt and xt prime is very much similar. So we are considering more and more frequency component. So you can see that xt prime and xt is almost similar. Okay, so this was our main goal for today's class, to verify that if we have a signal xt, if we perform the Fourier series, then we can find their frequency response, say at different frequency, what is their amplitude, how their phase is varying. So this is the time domain also plotting. So even if you just add all of them, you can return back your xt prime. So that was our main goal to demonstrate, and hopefully you have understood. Even if you do not understand, please go through the lab report. There are some resource materials also available in the YouTube. Also, I will be also available. If you want, you can also contact with me so that we can discuss. Okay. So thank you. Allah Hafiz, all the best for your upcoming exam. Assalamu alaikum.